Tuesday?
Sorry?
What other Tuesday you want to
Tuesday
do?
after spring break.
The Tuesday after spring break, they will not be here.
Okay.
Okay, so let's keep going with the Unruh effect. I don't have a call today, so I have to. Last day we were starting with the Unruh effect, in particular describing the geometry associated with accelerated observers in Minkowski spacetime. So I defined these right and left Rindor wedges and the set of coordinates associated to each of them. And remember that the goal was to build a quantum Fock representation using these right and left Rindor wedges that would correspond to the quantum representation associated to accelerated observers, uniformly accelerated observers. So the first thing we had to do is to write the Klein-Gordon equation in those coordinates and look for the solutions with positive frequency with respect to the Rindor proper time, because this tau. So this is what we did in some detail, and so this is what is here in the blackboard. So we were, remember, Rindor coordinates. I don't have them here, but yes, I have them. Where time tau. Now we are in the right way. The spatial coordinates y and the transverse coordinates y and z, because the acceleration is in the x direction. So the xt plane corresponds to the tau psi plane. We are looking for solutions of this type, which are of positive frequency with respect to that time. And the dependence in y and z is trivial because there is no acceleration in that axis, so it's just plane waves. But the non-trivial part appears in the xi dependence. So when we substitute this general form on the Klein-Gordon equation, we were left with this other equation, which is like a Schrodinger equation for the xi component with a potential. And we were able to look for solutions to this, and these are the solutions. Solutions are positive frequency, trivial plane wave behavior on the transverse coordinates, and the xi behavior is more complicated and is given by these modified Bessel functions with this index and this behavior. So the mathematical form is not that important. What is important is that we have exact closed forms for positive frequency mode with respect to the Rindor time. So with that, we can build the head of all these modes is really a basis of what we call the space of positive frequency for the Rindor guy, and therefore we can write the one particle Hilbert space and the Fock space, the Fock space that we can call the Rindor right Fock space. So a quantum field theory on the right Rindor range. We can do the same for the left one. So we can write the modes, which is, as I said, are essentially the same, changing the time by the left time and the xi by the left side. And therefore we can construct also the Fock space, the Fock representation for the left Rindor range. So I was mentioning that we can extend them out of the Rindor wedges with appropriate analytical continuation, and therefore we can complete a quantization of the whole Minkowski spacetime based on this guy and this guy. So we can complete a quantization as the tensor product or as the product of the right and left Hilbert Fock spaces. And the question was, now we have two quantizations. We have the standard Minkowski quantization that we saw in chapter 2, and this new quantization associated to accelerated observers. Now what I want to do is to relate them, and in particular ask what is the Minkowski standard Minkowski vacuum, how it looks like when represented on this other Fock quantization. This is what we want to ask. So how accelerated observers feel the Minkowski vacuum. This is the goal of this chapter. And as you know, for that, what we have to do is to look for the Bogoliubov transformations relating the two bases. And this is what I wrote here, the Minkowski positive modes as a linear combination of the right and left positive and negative frequency modes with the alpha and beta. So now we have two families of alpha and beta, one for the right and the other for the left modes. Because the basis of positive frequency modes are both right and left. And this is where I stopped last day. So this is the point that I stopped at. So we can just start moving from here. So what I want to do is to compute these alphas and betas, and when I have them, I have full information about the relation between the two Fock quantization. So what we want to compute is alpha R. So alpha R has the following indices. You know, alpha R is always going to be the, if you remember, it's going to be the Klein-Gordon product of the Minkowski mode on the positive frequency right Riller mode. So, you know, we have this linear combination. In order to extract this guy, I just have to multiply phi by this guy, because that will give me 1, we'll extract this coefficient. This guy is orthogonal to this guy, so that will be 0, 0, and 0. So I extract that alpha. So the Mogulyubov alpha coefficient will have the indices from this guy and from this guy. So the indices from the first mode and the index from the second. So this is what we have to multiply, where, remember, the brackets are just the Klein-Gordon product. To compute the beta 1, we just need to multiply the Minkowski mode by the negative frequency and add a minus, because the norm of the negative frequency, the product by himself, is minus 1. So Minkowski mode. So I should leave some space because I'm going to write the expression. So the beta R is going to be given by minus the negative frequency mode for in the right Riller wedge, product with the Minkowski mode. I will write solution in a second. And for the left one, the same. Changing right by left. Positive frequency. And I will write the beta there. So just, you know, the computation is you know, you just plug this mode there, and you put here the Minkowski modes, which are just plane waves, I to the e to the I omega t plus kx, standard Minkowski modes, and you compute the inner product with the Klein-Gordon form, and it's not automatic, but the computation doesn't have any new elements. So just let me give you the result. So let me put a prime here. So it's going to be 2 pi k O prime 1 minus e to the minus 2 pi omega a power 1 over 2 times plus minus x. You can check that yourself using Mathematica, is the best option. This is root square there, just in case it's not clear from the camera. For the beta coefficients, we have minus 2 pi k naught prime a e to the 2 pi omega a minus 1. The same factor. this guy is simpler. We just have is the same as the alpha left is the same as the alpha right, except that we have minus k prime. And for the beta, that will be minus the same with minus. Where this k naught and this kx are just k prime. Sorry. K prime is kx prime, k orthogonal prime, and k naught is just the frequency of that guy. So it's just the root square of k prime square plus the mass square. And this is explicit computations produce that. And this is, in fact, all the information that we need to relate the both quantizations. So this is, in fact, all the math that we need to know. We need to do. So we have alpha right, beta right, alpha left, beta left, and these are the expressions are not trivial, but we have them explicitly and in analytical form, so we can start doing physics with them. And this was obtained, as far as I know, first time from Fulling in 1973. So quite early. Okay, so as you know, now that we have alpha and beta, it's just straightforward to get our goal of writing the Minkowski vacuum, the standard Minkowski vacuum on this Riller Hilbert space, on the focus space of the right and left Riller observers.
Is that kx over there for vector?
This arrow?
No, the kx inside that norm. Is that for vector?
This?
Yeah.
No, this is the x component of that. So this is a 3-vector, has component x, kx, and the other two components, the y and z, is what I call transverse k orthogonal, because it's orthogonal to the direction of acceleration.
Okay.
In equation H, should that be beta r?
The
On the very right equation.
This is r. Thank you. Thank you.
So the cube perpendicular is two components?
Two components, y and x. And I call it perpendicular because it's perpendicular to the direction of acceleration, which is x in my convention. Any other question? So again, what we have now is two Fock representations of the quantum field theory in Minkowski spacetime. One which is associated to inertial observers, and another one which is associated to uniformly accelerated observers, one in the right wedge and the other in the left one. We have a state here, which is the standard Minkowski vacuum, and we want to relate these two guys, and in particular see how this state looks like there. So if that relation is given by some operator u, that we expect to be a unitary operator, the state Minkowski vacuum here will be some state in this space, and this is what I want to know. This is what I really want to write explicitly. But we know how to do that because we have alpha and beta. So we know from chapter 4, we know that this guy in the hill in here will be given by some normalization and will be the exponential of two particle states. So it will be 1 over 2 h bar the sum over I am just copying the expression in chapter 4. So let me do it. In chapter 4 I had here 1 and let me do it. Vij a dagger 2I a dagger 2j, this acting on the vacuum of the second Hilbert space. So now this guy in our problem, this guy will be the Minkowski vacuum. This guy will be the product of the Riddler left and Riddler right vacuums. And V, remember, V was just the matrix obtained multiplying alpha and the beta and the image of alpha, just to refresh your memory. So we have all the ingredients. All we have to know to do is compute V and then compute. So all we need to do is compute V ij using all that expressions, 5 to 8. So this could be an exercise. Just give you those beta, you plug them there, and you compute it. Maybe it's not simple because these are matrices, so you have to be careful. And but there is a faster way of computing V. Of computing V, and this is what I'm going to do. Here, ij, remember, are the labels of our modes. Here, in our case, the labels of our modes are omega, k orthogonal, and r or l. So this is the label that corresponds to I and j. So there is a faster way of computing that, and just tell you that it relies. So the key point for that faster way relates on the fact that 7 and 8, which is this expression and this expression, that from those equations, from equations 5 to 8, we can obtain the following relations. We can write beta, and this is going to be the key observation to simplify the computations a lot. So that the right beta can be written, is really proportional to the left beta complex conjugated, putting with k prime, and the factor is just minus e to the pi w omega a. So you just can't see that by inspection because the alpha right and the alpha left just differ by changing the sign of k, but the alpha k and the beta, the alpha right and the beta right just differ by this factor and this factor are different, but you know they differ just by e to the 2 pi omega because there is 1/2 here. So factorizing this, we get them the same. There is also a minus sign that is here and is not here. So this is the minus sign, and the k and minus k also matches whatever needs to appear there, if I am right. So this equation is 9, and we have a similar equation for beta left as in terms of alpha right. And you will see in a second that with this, I can easily obtain, without further computations, the matrix V that is working. Let me call this 10. Using the same arguments. If you just, by inspection, you can see that this is true.
And just so I'm keeping up, they're both, that's K prime and K prime. Both
Yes, in
primes
both
on the
sides.
left,
In
And
both
then
sides.
only one prime on the right side.
Oh, sorry. That is not right. Yes. Okay. Thank you. So it relies on the fact that from that is true, and these equations imply the following relation. So from here, I obtain the following, and I will prove in a second how to move from here to here. So the annihilation operator of the right Riller wedge for a quanta with frequency omega and transverse momentum k orthogonal. This combination acting on the Minkowski vacuum is equal to 0. This is not trivial, so I will show it to you. But once we prove that, then we will be very close to our goal. I forget that U there. So remember, this is a state that we want to know what is it for. So the state, the vacuum, this state there, and from now until I'm just telling to you that it happens that this combination of right annihilation operator and left creation operator annihilates the Minkowski vacuum. And this combination of annihilation left and creation right, this is a dagger here, annihilates the Minkowski vacuum. So I will, this is the key information, so I have to prove that for you. So I'm going to prove how to obtain these equations. So first of all, just from the definition of Bogoliubov transformations, it is true that the annihilation operator is right when written properly. The other Hilbert space is a linear combination this is not too difficult. Maybe I should leave it as an exercise so you don't get too bored. Yeah. Prove this. What do you think? Okay, let me give you a couple of steps and you so because otherwise it is too boring just me doing computations here. So first of all, this relation that minus star omega k orthogonal k prime. So first, this relation. This is just telling you that you can always write the right annihilation operators in terms of the Minkowski annihilation operators with the alpha and beta. So this is just this equation, this relation between modes and this relation between A's are exactly the same as we have seen before. A similar equation is also true for the left modes, for the left annihilation operator. Changing, so the same, changing right by left. So if you want, this is just the basic volume of relations. But a consequence is that, if I now take the right, this guy, and I act on the Minkowski vacuum, I know what happens. This guy is a combination of annihilation plus creation, or minus creation. The annihilation is going to kill the Minkowski vacuum, and only the second term is going to survive. So we are going to have only the second term minus beta conjugated, beta right conjugated A Minkowski dagger K prime acting on the Minkowski vacuum. I can do the same with the other expression. Acting on the Minkowski vacuum, it has annihilation and creation operator. The annihilation is going to kill the Minkowski vacuum, and I'm going to have this. Sorry. I have here, I am computing here the dagger of this. So I have to write the similar expression for this, and then take dagger. So the coefficient that survive goes with alpha rather than beta. And from here, getting the expressions that I was writing before, I should give this a color because these expressions are going to be important. It's just automatic because if you now take this, forget about for a second about u and u minus 1. I just keep u and u minus 1 to be rigorous because these space and these guys are different. But for a second, forget that they are there. So now if you take this guy and you do this, and you take minus this factor, this guy, so it's just what we have here, minus that factor, left omega. So what you are going to have is the integral in K minus beta minus the factor that guy. But remember that we have a relation between beta and alpha left, which is that, so this is going to give you 0. So this acting on the Minkowski vacuum is going to give you identically 0. I have to put a u to be rigorous. But just using, where I am using here equation 9 in this case. So it's just an identity.
In equation 9, should there be a minus k formula there in alpha?
Here?
Yeah. Because in,
No, why?
and then in this one you have a minus, so then you're using that for this.
Right. In that one I have a minus there. And but somehow that minus this.
The e to the 5
That
left over.
minus disappears. And now I don't remember why it disappears.
Is this related to this dagger and conjugate, or like there we have conjugate, here we have dagger? So is that related somehow?
I don't see. I don't see. It is possible that it has to do with the dagger. I did the computations a few days ago, and so that's a good question. So let me. So question is, what is that minus? I will check my more detailed operations and let you know. But so there is a minus here. A minus appears there. And that is very important, this minus. So, so this is true. So I will double check that minus to see if I have lost it. Just write in my transcribing my notes.
Does it come from when if you use 7 to convert from alpha left to alpha right, you get a minus, right? So
If you go to 7 and you say it again?
because on
But say
one
it
of
again.
these, yeah. So on the first term in our equation, right, we're going to have a alpha right,
Yeah.
and so on the next one we'll have an alpha left, right? So if we convert from left to right, that's where the negative comes from.
That
And
negative
7.
is on K prime.
Yeah. Oh, I see what you mean. Okay. Never
So
mind.
I have-
right. It's a different. Okay.
I remember doing carefully and finding all the minuses, but maybe I missed it copying my expressions here. Okay, so and similarly, one can prove the other one. So if you want, this was 11, and this is 12. So the statement is that this proves 11, and similarly 12 pillars. Similarly, you can prove. Okay, so this is the end of the proof, and now we come back to these equations. These are the key equations, and I told you that this is the information that we really need to obtain the V which tell us what we want to know. And in principle, V can be read automatically from here. You don't have to do any other computation. Let me just remind your memory from what we did in chapter 4. Recall from chapter 4 that there, for the general case, we had this expression. We had that expression, and in fact this is where you started the homework to prove this equation. So one of the homeworks were starting from here, obtain this. But from here, multiplying by the inverse of the matrix alpha, it is quite easy to show. So multiplying by alpha minus 1, it is quite easy to ij conjugated alpha minus 1 jk a dagger j is acting on u1 is equal to 0. I just multiply that by that, and this is what we call the ij. So this is what we did in the chapter 4 for a general case. But now what we have in our particular case is exactly an expression like this. These expressions are exactly of the type. So the b coefficients are just encoded here. We can directly read from these two expressions what b are. So I close here the reminder, and what I say is that then equations 11 and 12 imply that, are you able to read from here what is v? From here. I mean, it's not completely trivial because because v are really matrices, depend on the indices, and the indices, remember, I and j in our case, they are omega, each of them, omega, k star, and right or left. Yes. I and j both have really three parts. Omega, this is what we need to characterize each of our modes, if it is on the right or on the left, and what is the frequency and what is the transfer moment. So let me just tell you what is v for a given omega. Just a block, omega block of the matrix v. So implies that the basic blocks of the Vij matrix are of this type. The V matrix is something that, when multiplying our A's, give me this times the left one. So it's not difficult to convince you that you have to do this by yourself, because otherwise it's impossible that you are convinced. So minus e to the minus 5 omega over a times 0. So this is what I call a v omega block. So because essentially what you see there is that if this guy acts on the dagger right omega k and on the dagger left omega minus k orthogonal, you obtain precisely that. You obtain 0 times this guy. This is what I have here. This is the, it's like, if in this matrix, this is right, this is right, left, this is left, and this is left, left. So if you multiply this by this, you obtain precisely this term. And if you multiply this by this, you obtain precisely the other term. So think about yourself for a minute and convince yourself that is the case. But with that in mind, we have all what we need. I am ready to write it, what we are looking for. So I can directly write what is the Minkowski vacuum when expressed on this Hilbert space. Again, a normalization factor. I think I just erased the main equation where you have exponential of that. So just let me write the same using our V. So we had here sum in I and J. As I said, I and J now are omega and K orthogonal R and L. So omega is continuous, so I have an integral, and K is also continuous, so I have an integral. Everything goes in the exponent. And now, because this is quite simple, if you please just give me minus pi omega over A dagger right, omega K orthogonal, A dagger left, omega minus K orthogonal. This is the exponent. This is acting on the vacuum of our Hilbert space. And this is what we wanted to obtain. So this is our final result. This is really the core of the Unruh effect. So what I'm going to do now is to just expand the exponential so you can see more explicitly what that state is. So because it's the exponential of two particle states because acting on this. So it would be vacuum, 2 particles, 4 particles, 8, 6 particles, etc. The 2 particle states are not arbitrary particles, so are one created by this guy, one right together with one left, with K and minus K. So let me just write it the same, more explicitly. So, expand the exponential. So if you expand the exponential, the first term is just, is 1. So 1 acting on the vacuum is the vacuum. Plus 1 power. So we are going to have one of these integrals. So sum over all omega and all K orthogonal of a state with, this factor into the minus pi omega A. Remember, A is the acceleration. Now, one state with frequency omega and momentum K in the right Hilbert wedge cross one state with the same frequency and opposite K orthogonal in the left wedge. Plus 2 of these integrals two of these factors, one with omega and one with omega prime. Now I need more space. One quanta with frequency omega K in the right, one quanta with frequency omega minus K orthogonal in the left, one quanta frequency omega prime K orthogonal prime in the left, one particle omega prime minus K orthogonal prime on the left, plus dots. So vacuum, 2 particle states, 4 particle states, 6 particle states, etc. I can still write this in a different way, which will be useful later on. So the last way of writing this is just, rather than expanding the exponential, I can bring this integral to a sum outside the exponent and then expand. So first convert the sum in the exponent to a product outside a symbolic product because omega and k star are both and k orthogonal are both continuous, and then I expand the exponential. The three expressions are equivalent. E to the minus n pi omega over 2 this last expression is maybe the most graphic one. And I should write a big box here because this is the main result of this section. Three expressions for the same thing. So now let me comment on this expression, and then you can ask me questions about it.
Something related to entanglement. Related to entanglement.
For instance, this is good that you understand this step because the Hawking effect is extremely similar. The Hawking effect, we are going to do the same. Obtain the relation that I erased and find the B matrix, which is extremely similar, and write the state, which is extremely similar. So as I said, n is a normalization factor. So first of all, we have, and we'll wait until you copy so you can pay attention.
So is the third term there, so 0, 1s or 2s?
Here,
Yeah.
ones, but they have two of them. So I have this is if you want product. So I have two particles on the right way and two particles in the left.
Okay, so
But-
when you take the sum there, it goes from n equals 0 to infinity. Does that make that turn into 2s?
Here,
Yeah.
yes, but we also have the product. So you will have, choose a frequency, expand the sum, so you will have vacuum 1, 1, 1, 2, 2, 3, 3, and now you have to take that and multiply for different omegas. So the 1, 1 here will multiply 1, 1 there, and will give me something like this. You have exactly the same terms here, but here. Exactly
So that product is it like that product is sort of tensor product, or is it just product?
This is just a product. The way I like to think in the product is, take the A's, the creation operators, out of the vacuum and multiply that, leaving the vacuum outside of the product.
I mean, this is normal product, right?
So it's like a normal product.
Okay, that tensor product.
What happens to the integrals?
Right. So this is like a continuous product, if you will. So let me mention that because so the statement is that these intervals here, which are quite ugly, is an artifact of using as my basis plane waves. So if I had, if I come back and I use wave packets with discrete indices, then which is the correct thing to do because plane waves are not normalizable. So then this would be sums, and then it would be a product of discrete numbers. But the computation would be much more difficult because you have to involve all the time the wave packets across. So I think it's much easier to do it this way and then tell you, if you want, do it with wave packets, and at the end of the long computation, we'll have a sum here. That's all. So let me just write. So had we use normalized or normalizable wave packets rather than plane waves, the intervals, so peaked in some frequency, omega I now in that case would be discrete. The intervals are replaced by discrete sums. And that is the most correct way of doing it. But as I said, it's much less pedagogical. Now let me mention also that, so first point I want to mention, second point I want to mention is that Fulling in 1973 already shown that this state that we just have written is in fact not normalizable in the product space. What is the conclusion?
Then what is use of that n?
Sorry?
What is use of this n? What is use of this n, like if it is not normalizable?
This is just, that should be, if you compute the norm of this guy, I can do it if you want. This n would be the normalization. If this in fact has norm infinite, this should be 0. But that is just formal. That means that you cannot rigorously normalize the state.
So like, is there use, and like, why are we putting n then? Like, I mean, if state is not normalizable.
Because we didn't know it was not normalizable. So what I said, okay, I have a state. Probably this guy, I would like to have norm 1. So just let me add n such that it gets normalizable. And then I find that n has to be 0. So therefore, formally, there is no normalization. But
at this stage, if I calculate n, it will be a series in orders.
I can do it now if you want, just in a couple of lines. But let me first say the conclusion.
Yeah.
What is the conclusion?
It is like something like plane wave, and we
No.
have
It's not in the Hilbert space.
Right. So this state is not in that Hilbert space. Therefore, the two representations are unitarily inequivalent. So as we discussed in chapter 4 in detail,
this right side is FR in subproduct FL, right? The right side?
say it again.
The right side of, I mean, we are writing this. So the right side state, this representation, yes, this is in FR.
This is a state here,
so
in that Hilbert space.
Okay, so this is normalizable.
No. So we have the Minkowski vacuum here, which is normalizable, has norm 1.
Yeah.
And now we move it to this Hilbert space, and we ask if the state that we obtain, this state,
Yeah.
which I just computed for you,
Yeah.
we ask if it has if it's normalizable.
Okay.
So let me.
Yeah.
So this can be seen as follows. So you can, let me call, let me call this state alpha or gamma. So let me compute gamma. Just from here, if you compute gamma, you are going to obtain, you will have Dirac deltas, and you are going to obtain essentially the product that sum from n0 to infinity of 2 times that. You can do, because these states are orthogonal to each other. So if you just multiply this by the corresponding bra, you are going to get this factor. You can do that sum easily. That sum is just it's just a geometric series. So it's 1 minus e to the minus 2 pi omega over A, and you can see that this diverges. So the normalization factor should be the root square of the inverse of that. So 1 minus 2 pi omega over A root square. You can say, if you do with a product. You can see that goes to 0.
Is there an n in the first line?
Here,
The 2 lines between.
the other is a. Thank you. 2.5 omega over 8. That is that. So the conclusion that already Fulling realized 40 years ago, 43 in fact, is that therefore the Minkowski and Rindler representations are mathematically unitarily inequivalent. That U that we were assuming exists, it doesn't. There is no unitary operator related there. But also, as we saw in chapter 4, this is not a problem for doing physics. I mean, it's quite important conceptual problem that, one can show that as long as you focus only on a finite number of physical observables and your observations have some finite accuracy, so they are not perfect observations, then there is, in fact, a state here which physically corresponds to that state. So I'm just referring to the long discussion that we had in chapter 4. So physically, one can just put this problem aside and keep moving and do physical predictions. But it's important to keep in mind, for me conceptually it's very important to know that happens. Okay, so these are the two comments I wanted to make. Now let's discuss the state. So now the interesting thing is that the structure of the Minkowski state in the Rindler-Hiller space is quite interesting. So you can see, for instance, here.
Like if you fix omega and the k limit is entangled R and
Right.
for n.
Exactly. So what we have, we can pay attention to the second line if you want. We have that state, the Minkowski state is a very peculiar state. So it is made of superposition of two particles state. 0, 2, 4. And in each term, one of them is on the right Rindler weight, the other one is on the left Rindler weight. So this one is in the right, this one is in the left. This two-particle state is in the right, this two-particle state. So we really have, remember, we really have two causally disconnected wedges, the right one and the left one. And the Minkowski vacuum is just superposition of vacuum plus 1, 1 plus 2, 2 plus 3, 3. And not only that, but the one particle in the right one has, or transverse momentum k, is entangled with the one particle in the Rindler weight with momentum minus k. So in particular, I'm not going to write all that because I should get a raise of salary for that. Because I also teach in the morning, I write a lot, and after write so much.
And like for me, this last example was very much clear, like to see that. The last line.
The last one.
equation.
Good. So, but you are quite familiar with entanglement and with all that stuff. So I mean, the goal for me of writing the second line was just to add more information. But you can, of course, you can see that here. So that means precisely that, if now somebody goes and measures n particles in the right wedge, you can be sure that the state on the left wedge will have also n particles with transverse momentum minus k, for sure. So in particular, if you observe, so now you are an observer, you go to the left, the state is in the Minkowski vacuum, you go and measure, and you see n particles, L Riller particles. Because remember that these guys are Riller quanta, so are quanta with positive frequency with respect to the Riller time. So if you measure n Riller particles with frequency omega and transverse momentum k star in the right wedge, you are sure the state has collapsed to n particles, and again Riller particles with omega and minus k orthogonal in the left one. And in particular, note there is momentum observation. You know, because if you see here in quanta moving here, you find, sorry, in the orthogonal direction, you see minus k in the other side. So, you know, it's this equation I didn't give a name. I think I don't remember. I think it was 13.
Does that mean there's zero net momentum?
Say it again.
Does that mean there's zero net momentum?
Yes, because the Minkowski vacuum we knew it has zero net momentum. So.
Well, but a particle in the Minkowski vacuum could in principle have net momentum.
Right, but you know, the state that we are writing is just the Minkowski vacuum.
Oh, so it's a vacuum.
Right,
Yeah,
the vacuum.
so the vacuum
So
does-
the only thing is that when you write it in a Riller basis, it has all these, you know, all these really amazing correlations. So, you know, if you want, this expression shows in a very explicit way how non-trivial is the Minkowski vacuum. We believe that vacuum is, you know, is the most trivial thing. You know, it's highly non-trivial. It is a state which has this very peculiar entanglement between n particles on that wedge with n particles on that wedge. Entanglement between regions which are causally disconnected from each other. So you know, if you want, in this way, you are just going to the interior of the Minkowski vacuum, and you know, it is really manifest how non-trivial is the Minkowski vacuum inside. We already knew, you know, just remember computing the 2-point function in chapter 2, that the 2-point function of the Minkowski vacuum has non-zero correlations at the spatially separated points. So it's the only thing, you know, this is not a surprise. We already knew that that was there. It's only that this is really explicit, and this is really shocking, telling to you that those correlations are there. So a quantum state is something global, which has all these really precise correlations between different points, and in this case we can see that really explicitly. So I think it is, that expression for me is quite nice. But we are not still where we wanted. So there is a missing step. So remember that our goal is to describe, because you know, the Riller left and right are really causally disconnected. So are like two systems of references which has nothing to do with each other. They don't talk to each other. So we are just putting them together to complete the Minkowski spacetime. Our goal was to really write the Minkowski vacuum in one of them. So write the Minkowski vacuum in the left or in the right Riller wedge. That would correspond to what one of the observers would really measure of the Minkowski vacuum. So what we have to do now is take that state and project that state, or reduce it to the right wedge, for instance. So essentially, trace over the degrees of freedom on the left. So the last step to meet our goal is to project the Minkowski vacuum, which now is written in the focus space product of left and right, projected in the, for instance, in the right focus space. In other words, we have to just get rid of the degrees of freedom which are on the left hand side. So we will take trace with respect to the degrees of freedom on the left. So the way of doing this is the following. So this can be done first, constructing what we call the density matrix associated to the pure state, the Minkowski vacuum there. So the Minkowski vacuum is a pure state, but we can construct its density matrix just in this trivial way.
I have one question. Like, I feel, that product is it? We have their tensor product, right? Like omega and omega prime.
Mm-hmm.
So that should be tensor product, right? Like not just.
The best thing of thinking about that is to take away from the states all the creation and annihilation operators.
Yeah.
Put a parenthesis, put the vacuum outside, and then take products of that. So you will have many products of A and A diagram.
Yeah.
And then you act on the state again.
Yeah.
I think that is the cleanest way
Yeah.
of doing it. So this is the density matrix of the pure state U. I haven't done anything of that state. So there is a density matrix in the product space. Now what I have to do is to take trace of this matrix with respect to a basis of that. So what I want to do is to construct what we call the reduced density matrix. And now take partial trace in the left space. So this is what I'm going to construct now. Let me call now so let me call this row M because it's like Minkowski. And now I'm going to construct a new density matrix. Let me call U from Unruh, which is just the trace of the Minkowski density matrix on the product space on the left focus space. So this is going to be the sum for omega rho M alpha, where the sum is in a basis in the left focus space. So just construct the reduced density matrix on the right focus space. In fact, obtaining the result is almost trivial, just looking at that expression, because all you have to do is to get rid of these guys. And that's all. The only thing is that, question. What I'm going to get is going to be a pure or a mixed state, if you remember what is the definition of pure and mixed state. It's going to be a mixed state. Because we have a pure state on the whole Hilbert space. It's a pure state, this Minkowski vacuum. In both Hilbert spaces, it's a pure here and it's pure here. But now we find that there are correlations between the two wedges. So there is common information between them, and now we are forgetting about this guy. So we are losing information. When we are losing information, what is going to remain here is going to be a mixed state. Von Neumann already realized about that if you have a state in this room and you restrict it to observables all in this ball, the resulting state will be a mixed state because you are losing all the correlations between inside the region. So, can somebody tell me what is going to be that density matrix after taking partial trace?
The will be this product sum over and just right side.
So, n squared.
Yeah.
Now,
Like
omega, the product. So you have to take this, multiply by themselves on the get side, and then take trace on this basis. When you take trace on this basis, the two products are going to be eliminated, and the two sums are going to be eliminated because delta functions will appear, so you will end up with only one product. It's an ugly product which is continuous, but think that if you do it properly, it would be a discrete product. One sum, and now you will have just n particles in the Riller product with n particles in the Riller.
that exponential factor will be.
I forgot the exponent, sorry. Thank you. And the exponent with exponent squared, so it's going to be 2 pi omega over A n omega k orthogonal and so in the right wedge let's go omega k orthogonal in the right wedge, and this is the result that we really wanted to obtain.
Yeah, like,
And this is a mixed state. This is genuinely mixed state. So this is the Minkowski vacuum when reduced to the right Riller wedge.
so like just for notation, I mean, like for better notation, we could have written there R instead of U, right? Like
Say it again.
Like just for better notation, like we could have written R instead of U, right? Like rho R.
Right. I didn't want to do that because there is also a vacuum which is the Riller vacuum, and I was using R for that. So somebody may think that rho R may be the density matrix associated to the Riller vacuum. That is not true. This is the density matrix associated with the Minkowski vacuum when restricted to the right Riller wedge. So we can write here, if you want an R here from right, but not from Riller, and the U from Rho. Maybe there is better notation. Okay, so this is our final goal. This is what we wanted to obtain. Now we have to do physics and physically interpret what this density matrix is. So the guy in the Riller wedge will obtain all its physical predictions using this density matrix. You ask him whatever question, this is the density matrix that he will use to compute physics. So we have to physically interpret what
There will
this.
be n also, right, in exponential.
There is an n also in the exponential. Thank you. Thank you. Sum over n. Don't confuse pi's with n's, which are quite similar. So let me just interpret this result, and I finish this section, and we finish it. Any guessing of what that is? I told you at the beginning of the chapter. So I'm going to take that state, I'm going to manipulate it, to write it in a more familiar way. So first of all, note that h omega, I have omega in the exponent, so imagine that I divide and multiply by h. So h omega is the eigenvalue of, so please. What I want to do now is to focus on this guy here first. So omega is the eigenvalue of the state n omega in the Riller wedge. With respect to the energy operator to energy operator. So remember that the states in the right Hilbert space, they were positive frequency with respect to tau. So therefore there is a Hamiltonian, which is the Riller Hamiltonian, for which the energy of that state is just n times omega h. So with respect to the energy Hamiltonian associated to the killing vector field partial tau. So there is an energy Hamiltonian. Let me call it. So let me call it H Riller. Classically, remember, if you have a killing vector field, you can construct, in particular if it is time-like, you can construct a conserved quantity which has the interpretation of energy, just integrating on any Cauchy hypersurface the flux of the energy momentum tensor contracted with that killing vector field. So this is classically how you build that Hamiltonian, and the double dots. So this is just the quantum operator associated to this classical Hamiltonian. This is the energy definition for a accelerated observer. So this is what he will call energy. And these states have definite energy, where the energy is n times h omega, as you can imagine. For them, the Riller right wedge is stationary, is static, in fact. So they have a well-defined notion of energy, and this is the corresponding Hamiltonian, where the double dots mean that the origin, so that, right, normal order, the origin of energies has been shifted so that the Riller vacuum has zero energy. So this is the Hamiltonian, and we have just put the zero energy in the vacuum. So this state really has that energy because it has n quanta, n Riller quanta with respect to that energy operator. Then this orange stuff that I was writing there, 2 pi a over omega n times the state, is just, is just e to the I double dot this Hamiltonian divided by h bar. I have a factor here. Sorry. Divided by 2 pi a h bar acting on that state. If you act with this guy on the state, this is doing nothing, so that will be there. The operator acting on the state will give me n h bar omega, and I divide it by h bar to compensate because there is no h bar here. With that, I can write that in a very suggestive way.
Did you also have a 1 over omega squared?
1 over omega squared.
Because you're going to get a...
Oh, sorry,
h bar omega.
sorry. This is omega divided by a.
Right. Yeah.
So the omega comes from the Hamiltonian,
Yeah.
and a is there as before. Sorry. Therefore, with this information, I can write this Unruh density matrix as, let me just write n squared. We know what is n. I wrote it before here. It's just a formal density matrix. The product
recording something else.
They're looking at the window. No, they just zoomed in out.
Okay, now they're back.
So I can just replace this by what I wrote there into the I. Sorry. I don't need the I, isn't it? The I. Because there is no I here. So, I need a minus rather than a minus this times into the 2 pi a times these two states. State omega k thriller and omega k. But now the nice thing is that this guy is an operator, so it doesn't depend on omega, doesn't depend on n, so this product and sum doesn't do anything on that, so I can move it there. And what I have is a product and a sum of all the states in my Hilbert space, so this is an identity. I can take it out. So what I just show for you is that this is minus the Riller Hamiltonian I don't know why I have separated the exponential, because I don't really want to separate the exponential. I want to keep it together. So 2 pi a over h. So this is just n squared e to the minus this guy 2 pi a over h. This is what this density matrix is. Quite elegant way of writing it. Any suggestion? What is that?
What is this?
So, physical interpretation. Recall, if you go to your book of quantum mechanics and you see what is a thermal density matrix, so the density matrix of a thermal bunch of photons or of any kind of particles, a thermal density matrix is just, e to the minus energy, classically or quantum mechanically, k beta times t in the denominator, 1 over z, where z is just the trace of the thermal density matrix. But this is precisely what we have here, because you can check that n squared is precisely the trace of that operator. So we arrive at the remarkable conclusion that the Minkowski vacuum when restricted to the right wedge is precisely a thermal state at what temperature?
QVT is equal to 2 pi by EH cross, EH cross
Let me call it one more temperature, say it again.
KVT is equal to AH cross by 2 pi.
Right, so we have just, this should be 1 over the temperature times KTV. So equating both, you get that this KTV goes in the denominator. You also have a 2 pi in the denominator. In the numerator you have h bar a. And this is the, what we call the ultimate temperature. And And this is what we call the celebrated Unruh effect. So this tells us that precisely, when you take the Minkowski vacuum and you restrict it to the Riller-Hilbert space, the pure Minkowski vacuum becomes a mixed state, but not an arbitrary mixed state. Becomes exactly a thermal density matrix with temperature proportional to the acceleration given by this expression. So any observation that the Riller observer can make on physics will be distinguishable of having a state which is a thermal state.
I don't know what do you mean by thermal state.
A thermal state is, is this.
Yeah, but like physically, what is
Black body spectrum. So bunch of photons with black body spectrum, that is a thermal state by definition. Quantum mechanically, it is described by that. But this is more than the spectrum itself, how many quanta you have. This has all the information on the state. So any expectation value can be obtained from there. If you want to obtain the Planckian curve, you have to take expectation value with respect to the number operator or to the energy operator as a function of omega, and you plot it, and you will get the Planckian spectrum. This completely characterizes a thermal state. So now just let me finish. It's already 6. Okay, so I can just discuss a bit about this next day.
okay? So can we ask a question?
So let me finish. And so next day I will just add a few comments on that, and then go to the last section of the chapter, and I will finish the chapter, which is redoing this in a different way. Just forgetting about the Riller focus space, just considering, because this may be mathematical. You have two Hilbert spaces, one state, you go to the other, is a density matrix. And for me, it's fine, but maybe for somebody with more physical oriented, it's too mathematical. In the last section, what I will take is to consider Minkowski, standard quantum field theory, and a particle detector on it. So only one Fock representation, the Minkowski band. And that particle detector is going to be accelerated. And I'm going to compute what this guy is going to measure. So what is going to be the probability of excitations and de-excitation, as we did in the chapter 4, but now in a particular case. And I will show to you that this detector will measure things as if it was in an oven with that temperature. So as if it was surrounded by particles with that temperature. So, and I think that is a very physically transparent way of saying that this is not just mathematics, that this is physics. You take a detector, you accelerate it in Minkowski spacetime in the vacuum, and it will start detecting quanta exactly at the same rate as if it was in an oven with that temperature. I will go over that in detail next time. And to me, these two things, this mathematical clean computation, together with this physical interpretation, is what really makes this prediction outstanding.
But it can never be observed because
Sorry?
it can never be observed because A need to be.
A has to be very large.
Understood.
So you need. It can be, but you need accelerations which are fields. Some people say that that you don't. Some serious people that you don't even need to test the Unruh effect because it's an obvious prediction of quantum field theory. If you trust quantum field theory, the Unruh effect is true. Period. You can check that if you are bored and you don't have anything else to do. But it's simply true if you believe in quantum field theory. It would be nice for me somebody to text it.
Yeah, so I mean here this what is that called UOM, like this Minkowski vacuum, like after U. So yeah, rho m. So does it belong to FR tensor product FL or not?
No.
Oh,
Mathematically it doesn't. So this is the
okay.
formal density matrix as I was mentioning.
Okay. Yeah.
So mathematically they are inequivalent. This state doesn't belong to that state. But for all physical purposes, there is a state here which is indistinguishable from this state. So
But when you put U, it becomes an element of that.
right, but U is not, mathematically doesn't exist. U is
That's what we
And
said.
right,
here, like
exactly.
we didn't finally conclude what n is, right?
But and yes, I wrote it before.
Okay.
In fact, if you do the sum, it's 0. So it's
Oh yeah, like n is 0. I mean, like it is not.
right, but
Yeah. So like, so what does this mean here? I mean, like,
It's part of the
And
Hilbert
it's-
space.
right, that is part of the statement that the two Hilbert spaces are inequivalent. So
So like writing this road, is it beneficial? I mean, like if I'm comparing with thermal state, because I don't know what n is, like n is zero.
No,
I mean,
so the statement is now, if you know, all this is formal. This is the statement. All this is formal because U really mathematically doesn't exist. You cannot find U unitary, and this is really not a state on that Hilbert space. That is mathematically true. But now, as we discussed in chapter 4, there is a state in this Hilbert space which is indistinguishable from physical purposes, from this mathematical one. So you can take that as that state.
okay, so in like if I take that, then it means that like if I take trace over L, so whatever I'm like getting here rho U,
Right.
here, so I'll have something indistinguishable
From
in-
a thermal state.
Okay, so I'll get that.
Exactly.
Right? Okay.
So the way of understanding this is, first you know mathematics and you know that, for this everything is formal because you cannot make it rigorous because this U doesn't exist. But then you also are a physicist, and then you know that there is a state on that Hilbert space which is indistinguishable from this one. And if you go to measure in your lab, you couldn't distinguish it.
Yeah, I mean, so like just for representation's sake, I could have written like, I mean, I can say that okay, this is rho R, right? Or I can't make that statement. Like if two states are indistinguishable, so I can say that to be, I mean, like, okay, this is rho R.
Exactly. I mean that is the picture one is taken here physically.
Okay.
Right.
And
So even this is formal mathematically, you know that there is a state in that Hilbert space which is indistinguishable from this, and this is what I am calling rho R,
okay.
rho R U.
Just to be clear that I understand it, this is not actually black body, right? Because this is a scalar field.
I mean, it's black body. What is not is photons. So are particles from a scalar field. But
Right.
Mathematically, I would say that this is what characterizes a black body. If this is the electromagnetic Hamiltonian, is what Planck really had in mind. But you can extend that to any kind of quanta.
Okay, I thought black body spectrum was the particular form of the black body spectrum. I thought you got that out of the fact that there were two polarizations.
And then you have some degeneracy factor telling you how many degrees of freedom you have. So this-
Okay.
Right.
So-
I don't call it black body. I call it thermal density matrix.
Bosons,
And,
Yeah.
if you have
and-
bosons,
right.
then
You need bosons, and that's all.
Okay.
So, and the thermal density matrix is what includes the black body and any other law that you want to obtain.
Yeah.
So
That's
that is completely true here.
So how can we be sure that it's all of this thing is not an artifact of choosing weird coordinates? Like in Schwarzschild, we see that there are many coordinate similarities, but they are not there. But they are just artifacts of choosing a particular coordinate system. So here we have chosen a Rindler coordinate system.
Really
Maybe
observing
that
something
is
really physical.
because it-
You really can simulate that physically. And this is in fact,
Sex,
that is in fact the goal of the next section. So in case you have some doubt because of the Nath symbol here, just do the simple exercise of a detector accelerating in Minkowski spacetime. No Riller coordinates at all. No Riller focus space, if you want. Only one focus space, the standard quantum field theory Minkowskian focus space defined by inertial observer. And a detector in your hand which is accelerating with constant A, with uniform A. Compute the excitation rate and the excitations, and you will see that corresponds to a thermal spectrum. So that tells you that this is, and this is why it's called Unruh effect. This was done by Fulling and not in this explicit way, and Davis in the 73 and 74. Unruh paper was in the 76, and Unruh did this particle detector. And that point is where people really convinced that was a real physical effect. In all these mathematical, because they are inequivalent, so you are not sure if your maths are cheating you. But the Unruh picture is really what convinced you completely that this is a physical real effect in nature.
But regarding his comment, you cannot have an accelerated observer forever.
Right, but this is of course.
So
right.
what happens is you have
You will still have that. So
an inertial observer, suddenly you accelerate for a long time and then you stop.
then you have a density matrix, with a smear with the resolution in space and time of your detector.
Right.
But it still happens that you can still extract the thermal spectrum.
Why can't we have an
And even people have tried, circular acceleration. People have tried everything, and all these thermal results are there. So I mean, normally when you teach the cleanest thing because it's already complicated by itself. but all this thermality or that persists, or you can extract thermality even if your detector has finite size in space and in time.
Where can I read more about what a thermostat is?
In any book of thermodynamics, quantum mechanics, if you want to say, or statistical mechanics, you will find all this.
This looks like the canonical ensemble.
Right. You know, this is just Boltzmann stuff, you know, in terms of energy over temperature, but now we are in a quantum theory, so you have a thermal state, but it's exactly the same as a thermal, the quantum version of a Boltzmann thermal distribution with fixed seconds. If any other question? So I hope next day we will finish this chapter.
Okay.
So next day